You probably assume that when you ask an AI a question, something digital happens. Code runs, servers respond, an answer appears. Clean, invisible, instant. Here is what actually happens. Somewhere, in a building the size of a football field, thousands of specialized chips fire simultaneously. They draw enough electricity to power a small city. Fans the size of car engines push heat out of the building. Pipes can move enormous volumes of water through the cooling system just to stop the machines from melting themselves. And all of that has to happen in under a second, every time, at a scale that is growing faster than the infrastructure underneath it can handle. The AI industry has built its ambitions on top of a physical world that was not designed for them. And the gap between what AI companies need and what the grid, the water system, and the construction pipeline can actually deliver is quietly becoming one of the most important business stories of the decade. This is not a story about code. It is a story about what happens when an industry that moves at the speed of software collides with infrastructure that moves at the speed of concrete. Let's establish the basics, because the numbers matter here. A modern AI data center is not a server room. It is an industrial facility. Inside, you have tens of thousands of high-performance chips, GPUs, which are graphics processing units, originally designed for video games and now repurposed as the engines of artificial intelligence. These chips run calculations continuously, around the clock, every day of the year. Training a single large AI model can require months of this sustained computation. Running that model at scale for users requires even more. All of that computation generates heat, enormous heat. And heat is the enemy of electronics, so every data center is engaged in a constant battle to remove it. That battle costs energy on top of the energy the chips themselves consume, and increasingly, it costs water. Modern facilities pump water through cooling systems to absorb heat and discharge it outside. A large AI data center typically uses 1 to 3 million gallons of water per day, and in hot months, some push well beyond that. Now here is the scale. A single large AI data center today might draw 100 megawatts of electricity. That is roughly the needs of 60,000 to 80,000 average American homes. And the industry is not building one of these. Microsoft, Google, Amazon, Meta, and a growing field of competitors have collectively announced hundreds of billions of dollars in data center construction over the next few years. Individual campuses are now being planned at 500 megawatts, 800 megawatts, approaching a full gigawatt of continuous power demand from a single site. 1 gigawatt is the output of a large nuclear reactor. These companies want that power available, reliably, 24 hours a day, connected to a specific location, often within 2 to 3 years. And this is where the hidden flaw cracks open. The electrical grid is not a system you can upgrade by placing an order. It is a network of physical hardware, transformers, transmission lines, switching stations, substations, most of which was planned and built decades ago for a different pattern of demand. Adding a gigawatt of new load to that network is not a matter of flipping a switch. It requires years of engineering studies, permitting, equipment procurement, and construction. If you're into stories about the hidden flaws inside powerful systems, subscribe. That's what this channel is built for. Here is a concrete example of what this looks like in practice. In Northern Virginia, which hosts one of the densest concentrations of data centers in the world, Dominion Energy, the regional utility, has disclosed that it is managing a queue of power requests so large that some projects are now pushed well into the 2030s before a connection is even possible. In 2023 alone, the company received new data center power requests totaling more than 35 gigawatts. Its entire current generating capacity for the state is roughly comparable to that number. There is no version of that math that resolves quickly. The problem is not unique to Virginia. PJM, the grid operator covering 13 states and the District of Columbia, reported that its interconnection queue, the backlog of projects waiting to connect to the grid, had grown to over 3,700 pending requests, representing nearly 300 gigawatts of proposed new capacity. Processing that queue is taking years, and the equipment required to expand grid infrastructure, particularly large power transformers, is itself facing supply shortages. Lead times for certain high-voltage transformers have stretched to 2 and 3 years in some markets because utilities across the country and around the world are all trying to upgrade their systems at the same time. Now bring water into the picture, because this is where the local conflict gets very real. In the American Southwest, water is not abundant. It is allocated, fought over, litigated, and politically explosive. When a data center arrives in an arid county and begins drawing millions of gallons per day from local aquifers or municipal water systems, it is not drawing from a surplus. It is drawing from a shared resource that farmers, cities, manufacturers, and residents all depend on. The tension in Arizona is a clear illustration. The state has attracted enormous data center investment from Google, Meta, Apple, and others, drawn by available land, flat terrain, and grid access. But the Arizona Department of Water Resources has acknowledged that the pace of groundwater-dependent development is creating real allocation conflict. Agricultural users in the region are already facing curtailed water rights as aquifer levels fall. Microsoft's proposed site in El Mirage went through extended environmental review specifically over water impact. And in Arizona and neighboring states, other proposed facilities have also faced scrutiny over water use. The argument that technology investment justifies that kind of water draw is not automatically winning in communities where people can see the wells running lower. And that local resistance is not just a political inconvenience. It is a business risk that does not appear on most financial models. Here is the domino chain that breaks first. A technology company announces a major data center campus. The announcement is credible: capital committed, land acquired, equipment ordered. The company applies for a grid connection. The utility opens a study, which takes 18 to 24 months. The study reveals that the local substation cannot support the load. A substation upgrade is required. The upgrade requires a large transformer. The transformer is on a 2-year lead time. Construction on the facility has already begun. The chips have already been ordered. The building will be ready before the power is. The facility operates at reduced capacity or sits idle for months or years while the physical infrastructure catches up. In parallel, the local water authority flags that the facility's cooling demand exceeds what the existing municipal system can reliably supply during peak summer months. A supplemental water agreement is negotiated, which takes time, requires environmental review, and draws objections from adjacent agricultural users whose own water allocations are already under pressure. By the time the facility is running at full capacity, the timeline has slipped 18 months from the original projection. The cost has increased. The competitive window the company was targeting has narrowed. And somewhere in the financial structure of the project, returns that were modeled on a certain timeline are being recalculated. This is the business consequence that is underweighted in the current AI investment narrative. The dominant framing is that AI infrastructure investment is a straightforward capacity story. Spend capital, build compute, generate revenue. The constraint on that story is assumed to be chips, or model quality, or competitive positioning. But the constraint that cannot be purchased away, cannot be accelerated by hiring faster engineers, and cannot be resolved with a better product is physical infrastructure. You cannot negotiate with a permitting timeline. You cannot acquire your way to a shorter grid interconnection queue. Some companies have understood this earlier than others. The movement among major technology firms to secure long-term power agreements with nuclear facilities signing multi-decade contracts with operators of existing plants, and in some cases exploring partnerships with operators of mothballed ones, is not primarily an environmental positioning decision. It is a supply security decision. Amazon has a 20-year power agreement with a nuclear plant in Pennsylvania. Microsoft has pursued similar arrangements with nuclear operators in Illinois. When a software company starts structuring its business around 20-year power contracts, that tells you something important has changed. What these companies are buying is certainty. Dedicated, uninterruptible electricity that does not depend on a strained public grid or a utilities upgrade schedule. That certainty is worth paying a premium for, because the alternative, building a data center that cannot be fully powered, is worse than paying more for electricity. But not every company can afford dedicated nuclear arrangements, and not every region has plants available for that kind of deal. Which means the AI infrastructure build-out is quietly stratifying into companies that secured physical resources early and companies that are now competing for what remains. Land in favorable grid markets, water rights in viable locations, utility agreements in regions with spare transmission capacity. These are not software assets. They do not scale instantly. They do not get cheaper with iteration. They were, in most cases, not priced for what the AI industry is about to demand of them. For investors evaluating the AI sector, this creates a specific analytical risk. The financial models built on AI infrastructure returns typically assume capital deployment translates to operational capacity within a defined window. What the infrastructure bottleneck introduces is schedule risk, cost overrun risk, and regulatory risk, all of which are correlated because they all emerge from the same underlying constraint. A portfolio of AI infrastructure investments that assumed smooth grid connections, timely water permits, and available equipment is a portfolio that was modeled on conditions that no longer fully exist. The broader economy will feel this too, though less visibly. Industrial electricity consumers, manufacturers, chemical producers, food processing facilities have already begun raising concerns with regulators in Georgia, North Carolina, Texas, and other states about the impact of data center load growth on their own power costs and grid reliability. When utilities invest heavily in infrastructure to serve large technology customers, those investment costs eventually flow through to rates paid by all customers on the system. This is how a data center outside a city begins to affect the electricity bill inside one. The AI boom is not a story that ends badly. Grids have expanded before. Infrastructure has been built to meet demand before. New generation capacity is being planned, and some of it will arrive. But the pace of physical infrastructure development has a ceiling that software ambition does not. And the companies, investors, and policymakers who treat that ceiling as a temporary inconvenience rather than a structural constraint will encounter it more roughly than those who planned for it. The next phase of the AI race is not being run on cloud servers. It is being run in utility commission hearings, water rights negotiations, transformer procurement queues, and substation upgrade timelines. The companies that win are not necessarily those with the most advanced models. They are those that understood early enough that the most valuable thing in AI infrastructure right now is not a chip, it is a confirmed power connection. If this changed how you see the AI boom, subscribe and tell me in the comments what you think breaks first: power, water, or permitting. The world was not built to feed this machine at this speed, and the machine is just starting to get hungry.